the ICTP-SAIFR IFT-UNESP colloquia series. It's a weekly colloquia series. And so usually we organize schools, and things that we do during the schools is to invite one of the lecturers to give a seminar to the IFT community, which is not only working on this topic of the school. This particular school is on observational cosmology. And last week we had a colloquium on unveiling the nature of dark matter. And today we're going to have a colloquium about unveiling the nature of dark energy. So it's a pleasure to introduce you Professor Alessandra Silvestri from Leiden University, the Institute Lawrence. I hope I pronounced it correctly. And so Alessandra did her PhD at Syracuse University, and then a postdoc at MIT, and then a brief stay at CISA before joining University of Leiden. She's well known for work on dark energy, more specifically modified gravity models. And it will be a pleasure to hear her talk about unveiling dark energy from the large-scale structure, the theoretical side of the challenge.
Thank you. Thank you for having me here. I'm really enjoying this week here, though it's an intense one. But OK, so it will be a bit of repetita juvent for the students that are at the school. But there's also a spoiler for tomorrow's lecture, so I hope it will be interesting. Yeah, so as Rogerio said, I work mostly on dark energy, which is the problem, the name with which we address the so-called phenomena of cosmic acceleration, the fact that a few billion years ago, the expansion of the universe has started to speed up, contrary to what we expected, for it to slow down, if you want, roughly speaking, because of the pull of gravity from the matter in it. And we don't seem to have a good, while we are pretty confident on the observational side that this is going on, we don't seem to be so happy with our theoretical understanding of this phenomenon. And there's many different missions that are launching, are undergoing, etc., that are collecting data with different scientific goals, but typically dark energy and unveiling its nature is one of the main scientific goals of these missions. So I'd like to start with this slide where I show a picture from Leiden, actually. It's a wall in Leiden. So we have this thing of, there's a lot of poetry. If you walk through Leiden, there's a lot of poetry on the walls. And now some colleagues of mine started to also put formulas relevant, like that were sort of equations that are related to important physicists that were in Leiden. So Einstein was a visiting professor in Leiden. And so recently they made this beautiful wall formula on one of the museum. We have also, there is a very funny one, there is the Lorentz contraction, because Lorentz was, of course, from Leiden, working in Leiden. And if you are on the train, at some point on the wall of one of the buildings by the train track, there's a circle that transforms in ellipsis and then back. And there's the Lorentz contraction. You can experience it at slow speed, going back and forth. OK. So anyhow, I like to think of general relativity and the formulation of general relativity by Einstein in 1915, a century ago, as the time when we were finally provided with a theoretical framework that allows us to really address from a scientific point of view the universe and all the phenomena that we were observing there. So I like to think of, we like to think of that time to coincide with the time when cosmology became a physical science, when the era of physical cosmology started. And since then, it has been a very successful one. There have been many, many different observations, in particular in the last few decades, of things out there. We have picked up radiation, photons, reaching us from very back in the past and bringing a lot of information about the universe, mostly the early times, but also picking up something on their way, information on what happens later. Light, as Einstein told us, is banded by intervening mass. So if you look at distant sources, and in between you and those sources, there's some cluster, some big mass, the light will be distorted. There's many interesting things that you can do with this lensing phenomenon. And here is a picture of Mostly I want to focus you on the weak lensing part, which is the ellipticities, the shape of the galaxies to be slightly deformed, but they are typically already elliptical, so it's not exactly the ellipticity that you're after, but the correlation of the ellipticity of different galaxies around the source. And there's, of course, we start from a very homogeneous universe with very little fluctuations. Like here, you see little fluctuations in the temperature of photons as you look at in different directions on the sky. But those, through the billion years of the expansion history, grow under gravitational instability. And eventually, we are able to start forming structure. Dark matter that you heard about last week starts forming halos, and visible matter falls into these halos and starts forming the galaxies that we observe. So there's a lot that we have learned, and this is an idea of how this formation, the structure formation process goes on. And out of all these wonderful measurements, we have formed the so-called standard model of cosmology, also called lambda. I'm a bit sloppy here, should be a lambda, lambda CDM, where CDM stands for cold dark matter. So it's what the colloquium last week was about, and it's what we need to sustain clustering, to form the potential wells where matter will fall and form all the things that we observe. And there's another component in this standard model of cosmology, which is the one related to cosmic acceleration, and the so-called cosmological constant in this model. So, but as I was saying, we have learned a lot. We are pretty confident about many things, about this Big Bang sort of scenario, where we have at some point the release of photons out of the very early hot and dense configuration of the universe. At some point, photons decouple. They are free to travel to us, so they give us a sort of snapshot of the universe at its birth. And a universe that was originally dominated by radiation, but non-relativistic particles, becomes gradually dominated by matter. And that's when the pressure of radiation becomes negligible and structure can start forming because there's no pressure working against it anymore. And so you keep going and things form, and we are here today. And you see that the mystery that I was talking about, this speed up happens at late times. It's a few billion years ago. The dynamics of this expansion changes. This is one way of looking at all that we know about the universe. Another way is the very popular cosmic pie, a pie that Einstein for sure didn't want to receive on his birthday, but because there's a lot of darkness in it. So this is looking at if we rely on general relativity as the correct theory to study our universe, and use all these observations, this is what we conclude about what should be out there right now in the universe. So there is visible matter, the ordinary matter, the thing that we are familiar with, and we would have perhaps naively thought that was all. But then you need roughly a third of what is currently out there to be in this form of dark matter, for which we are pretty confident that it's probably a particle, but we haven't found it yet. And another 2/3, 68% roughly, in the current energy budget, to be either a cosmological constant or something that is there, becomes important at late times, and gives the necessary type of dynamics that you need in order to speed up the expansion of the universe. We call it dark energy, or in the simplest case, it's a cosmological constant. So typically, if you work on this puzzle, you work with the late, what is known the dynamics of the late universe, the last few billion years in the expansion history of the universe. And just to, again, stress the fact that cosmology so far has been extremely successful. And one of the main players in that was this radiation reaching us from early times, and just basically looking at the temperature of these photons in different directions in the sky. So here with the blue, yellow, and red, you see the different temperature, and fluctuations are really tiny, 1 in 10 to the 5. We can build out a spectrum, a power spectrum of this. So looking at how much anisotropy there is on an even angular scale. And this is this very famous angular power spectrum for the cosmic microwave background. And there's a lot of things that we have learned out of that. And in particular, we have learned about the geometry, the spatial geometry of our universe, to the point that we are pretty confident that it's a flat geometry. That doesn't tell us necessarily about the topology or the finiteness of the universe, but we are pretty confident that at least the visible universe is spatially flat. And then we have learned also a lot about how much of the ordinary matter that we typically call baryons is there, how much of total matter, so comprising also dark matter, we need, etc. So this was wonderful achievement out of the cosmic microwave background. And we also, since those fluctuations are really small, and also if we look at, yes, we live in a pretty clustered universe, right? We have a lot of structure around us, but if we zoom out, we see a pretty homogeneous and isotropic universe. And we're pretty confident about that. So the first simple thing that you can do is say, okay, I live in a homogeneous and isotropic universe. It's the same in each point, in each direction, but it's not static. It expands. And in then general relativity suggests you to use a metric to describe this spacetime. And if you have something that is homogeneous and isotropic and does simply a dynamics that such as expanding, that's the simple metric that you associate to it. You cannot put much else in here. And then think of sitting galaxies on a system of coordinates that you will call comoving coordinates. So think of embedding this universe with a system of coordinates that expands with it. Those are called comoving coordinates. Two galaxies, then, if they don't have any intrinsic motion, they move apart only because of the Hubble flow, because of the expansion of the universe, will sit at a fixed x coordinate, at a fixed value of the x coordinate in this system, because it's the system that is expanding. But the physical distance between the galaxies will grow in time, and will grow as determined by this scale factor here. And then if you do a little math and you look at how this physical distance between the galaxies changes in time, you find that it changes in a way that is proportional to the distance, and that's what Hubble told us. That was the first, if you want, experimental evidence that GR was a very good model for the universe. The distant galaxies are receding from us with a velocity which is proportional to their distance. Now, what Hubble measured were kind of close by galaxies, so it was really looking at the constant here. This function here is not the constant, it's our below Hubble parameter. It gives you the rate at which the universe is expanding, and that changes through time. But if you look at something that is not too far from you, you will see a constant in there. So this is the famous Hubble diagram. This is a more recent, there was an older version with the original measurements from Hubble. And then, of course, you fast forward, and you go to 1998, and two teams use the supernovae, and look, supernovae are like bulbs for which you know the intrinsic luminosity. You know, they have all the same luminosity. You buy a box of bulbs, and then you put them 1 meter from you, 2 meters from you, 3 meters from you. The light, the luminosity that you measure, of course, changes with the distance. If they all have the intrinsic luminosity, the further that bulb will look dimmer. And that's something that we do with supernovae. Very roughly speaking, of course, there's a lot of difficulties in there as well, but you can think of supernovae as standard or standardizable candles, something that because of the mechanism with which they form have an intrinsic luminosity that you know. And then you look at the flux reaching you from these supernovae, so you measure a luminosity, and from there, from comparing the intrinsic and the measured luminosity, you infer their distance. Simultaneously, you measure also the redshift of the galaxies that host this supernova, and then you have a measurement of the distance as a function of redshift. And that's a sort of modern way of looking at the Hubble diagram, again, at looking at how the universe is expanding. In 1998, they made these measurements, and they established that baryons, or like ordinary matter and cold dark matter, were not enough to explain the dynamics of the universe. the expansion started to speed up. We were living in a universe that was decelerating in the past when dominated by matter, but has started to accelerate at some point. It was, if you want, a huge surprise, although it didn't come completely out of the blue. There were already other indications from simulation of structure formation that were hinting at the fact that that might be the case. And then a Nobel Prize has been given to this discovery in 2011. It's also because many other independent probes have sort of confirmed this. So now with cosmic microwave background cluster and many different other measurements that we do in cosmology, we are pretty confident that the fraction of matter and the fraction of whatever we need to source it as acceleration are both different than 1, and in particular, we need roughly 70% of dark energy today in our universe. Okay, so we've learned a lot, and of course, as every nice story, with the progress in observations, and as your measurements become more and more precise, you also start seeing funny things. So this Hubble parameter that has been there since Hubble, it basically has characterized the history of cosmology. There's almost always been debates about the value of Hubble. It used to be, whether it's 20 or 100, I don't know, very disparate values. Now we are getting to it. It's somewhere around 70 kilometers per second inverse megaparsecs. I should mention that the value of this parameter today gives you also a hint about the age of the universe. And it's a very important scale in whole cosmology, right? So there's several different ways in which you can measure this parameter. Supernovae is the distance ladder is one of the techniques. And there's other things such as lensing effects, strongly lensed quasars, and many other things that are so-called late-time universe probes. You're looking at things not too far away from you. And you're looking at this Hubble diagram for supernovae. You're looking at how a quasar is strongly lensed, so you see multiple images of a quasars, and et cetera. And you reconstruct this Hubble parameter. Then there's other ways in which you can infer it, which is like the cosmic microwave background. Cosmic microwave background, I told you, is a snapshot of the universe at early times. Then you need a theoretical model to forward those initial conditions to today. So there is some dependence of what you infer for Hubble, for the Hubble parameter on your model. These are other independent probes that are also sort of anchored at early times, but independent of the cosmic microwave background. And you start seeing a pattern. This is just out of a very recent conference. I think we were mentioning it last night at dinner. And you start seeing this puzzling pattern where whatever is somehow related to early universe in terms of probes tells you a value for Hubble parameter. Whatever is related to later universe, and this is a combination of different, in principle, independent late universe measurements, starts telling you a different value. And with the error bars that go down, this starts being tantalizing. It's not necessarily a crisis. It might be still some systematics, although I think people are really working very hard. And so, of course, it leaves always the option of maybe there is some new physics. Because especially in here, in going from my early measurements to today, I have to assume a model for my universe. And so I just want to reinstate how difficult it is. So I told you, think of the wonderful measurements of this temperature of photons as a snapshot of the universe at birth. And then you keep going and structure form. And I always like to think of it as having the picture of a baby, very, very focused. It's on my baby. But this is my grandmother. So having a picture of a baby, very full, high resolution at birth, and then somehow knowing the later state, right? You now have a grandma. And in between, there's a life. And there's many paths that this life could have taken. And that's the analogy I like to think about when I look at the universe. We have a wonderful snapshot at the early times, and now we are seeing its state in the final years, all this structure around us, and we are improving with the resolution with which we are resolving this structure. So we are sort of understanding what it looks like today, though there's billion years. It's not just a lifetime, it's billion years in between here and here. And our model, our theory of gravity, plays a fundamental role in the path that we take in going from here to here. Every different path will give you a slightly different prediction for the distribution of galaxies out there in the sky. So let me show you. This is courtesy of Marco Baldi. He's somebody that is heavily involved in M-body simulations for models, both the standard models, but also alternatives to the standard model. This is a snapshot of a given simulation for structure that you observe at redshift 0, so it means today. And this is for the standard model of cosmology. And then you do it for a pretty significant modified gravity model. And yeah, it's more or less the same. But those are the tiny differences. So there are differences. And we are getting, with the current precision, especially in the next few years, we are getting to the point of starting to pick up these tiny differences. The thing is that what we have to do, and where we are still lagging behind, is to get ready to understand what is the correct theory that took us. We are probably resolving this state. We are solving perfectly the distribution of galaxies. Do we have the correct theory that takes us from that initial state to this? And that's what I'll try to tell you about. We don't have the solution yet. We are working very hard to make sure that we interpret whatever measurements that we will have in the best way. So I talk a little bit about supernovae and expansion history and the fact that you have this scale factor here. There's more that we can measure, as I showed, right? There's this structure forming. We can measure it. We can look at the galaxies, the clusters that are out there, their distribution at different distances, different positions in the sky. We can look at the ellipticity of the galaxies, whether they are aligning around some sources and so on. And so whether we are looking at the rate at which the galaxies form, the structure on these large scales form, we are looking basically at something that is probing this perturbation to the time component of the metric. So I told you, you start from an isotropic and homogeneous universe. The only variable that you can have in your metric is this scale factor, the function of time. But then you realize that, yes, that's a good approximation on the large scales, but we are here, right? So there's more. There's inhomogeneities in the universe. So let us start perturbing the metric. And as long as you deal with matter, its distribution, its way of growing, its bending of light, all you need to worry about is two functions perturbing your metric. And this function here is the one that determines is related to the dynamics of non-relativistic particle things if you want to move slowly. So it's very plausible that this is the component that is mattering more in their equations. Relativistic particles that are something of zero or very small mass. Yeah.
Once you allow x dependence, why don't you allow other terms in the metric?
So I don't allow, I could have tensor and vectors, or you're asking about scalar? Yeah, no. Okay, so tensor and vectors, yes, they should be there. It's just I want to focus on large-scale structure at linear level. And so at linear level, they decouple, and the one that is relevant for the one that is coupled to matter are only the scalar perturbations. Yeah. I'll bring a tensor in the game later. Yeah, and then I have only two because of the gauge fixing. And so one is related to the clustering, and one is related to the relativistic motion. So it's related to how light bends. And I keep repeating this, I think, every lecture that I'm giving. So, and you can think of when you look at non-relativistic dynamics, you should, if you want an analogy with what was done as on local scales with solar system of gravity, at studying the orbits of planets. And then if you do something like Eddington, you are looking at, for instance, weak lensing and other things. So there's light deflection and time delay effects. Now, we are, as I kept saying, we are out there measuring with higher and higher precision these galaxies, their lensing, etc. And that will open up a new interesting regime for testing gravity. So we have test gravity, general relativity as the correct theory of gravity. We have established it, sort of, through many different measurements. PPN is the post-parametrized Newtonian approach that was used for solar system, convincing ourselves that GR was the correct theory. And there's, of course, right now we have gravitational waves. This is sort of, it's a nice plot that shows the different regimes in which you can probe gravity in terms of curvature and strength of the potential. And large-scale structures are in a very different regime with respect to other observables. So it's a new territory. Now, what do we want to, how do we want to test whether our standard model is the correct one, whether general relativity is the correct theory of gravity, also when you go on these very large scales, and hence we have to live with something that is a cosmological constant, or whether we can do something else and substitute the cosmological constant with perhaps either a dynamical field or modifying the theory of gravity. Not in this, usually not in the same extreme level with which Einstein modified Newtonian gravity to explain Mercury's orbit, but still we might want to correct the laws of general relativity on the very large scales and maybe get rid of this embarrassing 70% in dark energy. Now, I want to discuss how we can use large-scale structure, this clustering and lensing to test such things. So let me just remind you all of what we know about growth of structure in the standard model of cosmology. So standard model of cosmology, as I said, that you source acceleration just with a cosmological constant. What is giving this cosmological constant is an entirely different question. We like to associate to the vacuum energy of quantum field theory, and there's an entire other set of problems, but if I have a cosmological constant, then that will be, I can think of it as a fluid out there, which is everlasting, something with an energy density that does not dilute as the universe expands. And the technical way of saying that is that it has an equation of state. This is relevant for how the Hubble parameter depends on time. An equation of state equal to -1. OK. Then I go beyond that. So you can use supernovae, for instance, for testing this, whether my expansion goes accordingly to something that is like W equal -1. I can go beyond that. I can use the clustering. So I can look at this potential, these perturbations to the metric, and perturbation in the distribution of matter. There will be more dense regions and less dense regions. And I can study how these behave through time. And the standard model of cosmology happens to be a very simple case for this. I know that the expansion history goes like W equal -1. And I know also that there's not much freedom out there. The two metric potentials are basically the same. So lensing, clustering, whatever, I'm measuring the same thing. And there's a Poisson equation. Here I'm in Fourier space. So this k squared comes from the Laplacian. From real space, I have gone to Fourier space. And so this is just a way of writing the standard Poisson equation. We are used to it also in Newtonian gravity, right? So the outcome of this in words is that lambda CDM not only has a very simple expansion history, but also a very simple growth pattern. And there's several characteristics of this, but in particular, each perturbations, once it enters into the horizon of causality, it will grow at the same rate, no matter what the wavelength of this perturbation is. And that's very peculiar of lambda CDM. So we have learned that it's very peculiar of lambda CDM because we have played around. We have looked at other models. And so similarly to how, to what we do for background, so when we use things such as supernovae for understanding the expansion, we use a function, the equation of state, and we leave it free, right? It will be -1 if I have the cosmological constant. It can be a function of time, not of space, of course, because I'm looking at the background that is homogeneous and isotropic. And then we use all those data to learn what W dark energy of A could be. It's very close to -1. Maybe it changes a little bit, and whatever. And then I go to the level, at the level of perturbations. And I can do the same thing. I can say, I have these perturbations to my metric, to my matter. In the standard case, I know they're very simply related to each other. Phi is equal to psi, and there is a Poisson equation. Let me introduce deviations from there. And I introduce it in terms of two functions. And now they have to be functions not only of time, but also of scale, because I'm looking at perturbations on top of an expanding universe. So there you go. Now we have expanded out of instead of going only at background probes and looking at W, now we want to look also mu and sigma and possibly understand whether they are 1 or whether they're not 1. And then I have to think, oh, this is not relevant for this talk. So I want to show what we have currently for W and what we will have in the next few years for W. This is a very nice plot. It's actually from the 2015 release of Planck, but it didn't change much with the latest release. They just had wonderful color in the 2015, so that's why I used that plot. So W, this equation of state that tells you about the dynamics of the universe at late times, can be a function of time if it's not -1. If it's -1, you are here. If it's a function of time and you want to learn something about it from data, you have to choose some dependence on time and fit to data. And the typical thing that you will see is that a Taylor expansion in the scale factor. So you have W, which is a constant, plus a linear factor in time, if you want, in the scale factor. So WA is that coefficient. And this is what Planck, these are contours, confidence contours. Never mind the colors, they're associated to the value of H0. So these are confident contours that tell us what Planck is measuring for W0, WA, perfectly consistent with the lambda, with the cosmological constant. The thing is that now we have other missions going out there, and since I'm from Europe, and in particular from the Netherlands, that is heavily involved in Euclid, I'm going to mention Euclid. Euclid is an ESA-funded mission with also participation from NASA. It will go out there, it will launch hopefully at the end of 2022. And it will measure billions of galaxies out there, their shape, their redshift, etc. And we will learn a lot. There's other mission that I should mention, LSST, DES that is ongoing, etc. It's a huge effort, international effort. So now this is from a forecast of Euclid combined with Planck, how it will shrink. You shouldn't focus on the position. There is a bias in putting it in -1, 0. We can bet on where it will fall. But the thing is, compare the size of these ellipses with that of the white one. That's how much more accurate the next measurements will be, how much we will learn about W0 and WA, for instance. That's great, but the main question that I'm trying to answer is, wonderful. You tell me that W0, WA is something that is not -1, 0. You have this tiny region. Do I have any idea about what theory is behind that? That's the question, because we can keep giving wonderful numbers for W0, WA, and then we do it also for mu and sigma, those other functions. But we tend to forget about the link with theory. So, of course, you tell me, well, why do you worry? It will be -1, 0, end of the game. That could be the answer. I would like also to argue that the answer that you get out of your data depends somewhat also on what you fit to data. So W0, WA might not be the best thing that you want to fit to data in order to let your data tell you something. Okay? You might be fitting something that is not really the right thing, and data will run back to -1, 0 and say, I'd rather stay there. You're proposing crazy things. But maybe you're forgetting to propose to data the correct theory. So, but mostly indeed is, if we don't hit -1, 0, say that we hit this point here, we have no idea of what is behind there. And the other thing is, and that goes to the question that Nathan asked, there's more out there. there's not just galaxies and their lensing, etc. There's not only the cosmic microwave background. We are measuring with increasing precision the polarization of the cosmic microwave background, but also we like to say that the era of gravitational wave astronomy and hence cosmology has started. It has started a couple of years ago, not only with the first detection of gravitational waves by LIGO, but also with the subsequent detection of gravitational waves with an electromagnetic counterpart. And that allowed to do very nice physics and allows us to learn something also about all the models with which we were playing to try to explain cosmic acceleration. And so the current framework that I showed before, those functions W, mu, and sigma, they're not able to absorb all this complementary information that we can get from things such as gravitational waves. And they're also very far from theory. So that's the whole thing that we are trying to work on. Yeah, this is just to show you one thing that we got out of this wonderful that they got out of these wonderful measurements of gravitational waves. In particular, once they picked up the electromagnetic counterpart, they could really sort of understand with good precision the location of the source of these gravitational waves. And that allowed, among other things, to measure the speed with which this gravitational wave reached us. And that turned out to be, surprisingly or not, basically the speed of light. And this bound here sent people really in a frenzy. And so speed of gravity being equal to the speed of light had quite some implications for the things that you could do when you want to modify gravity. So I'm not sure how much more I will be able to cover, but that's the sort of take-home message. That is, I hope I convince you that we will have wonderful numbers. We are out there measuring many good, very nice things. The questions that worry me is, will we be able to extract the correct physics out of those numbers? And we will be able to exploit all the probes that we will have, so also those that are associated to tensor modes. And so in the next, in the final part of the talk, I'll try to show you a little bit on how we are going in that direction. And so the question is, where do we stand on the theory side? We have progressed impressively on the observational side. We were shocked by this measurement and this establishing of the accelerated expansion. How much progress have we made on the theory side since 2 decades ago when accelerated expansion was discovered? And that's the progress. So that's how hard theoretical cosmologists have worked in the last 2 decades. And it's like a Russian doll system. I mean, each of these nodes here have more models inside. And so you can source cosmic acceleration with the cosmological constant, but I hinted at the fact that there are some problems, some questions that we might want to answer from the theoretical point of view associated to the value of this cosmological constant, and they might bring us to scenarios such as landscape. Otherwise, you can go somehow like Einstein did and try to modify your laws of gravity, or you can go like Leverrier did and try to predict a new planet. In this case, predict an extra component out there in the universe. And then you keep going. And you keep going, and you keep going. And there's more and more theories out there. And it becomes an hopeless gravitational landscape, especially because almost none, you can have a favorite. Some have, are better than others in terms of certain criteria. I argue at the school that I like a lot such models that are called degravitation because they try to address the problem of vacuum energy. But there's really no compelling front runner. From the theoretical point of view, we don't have strong arguments to believe strongly in one of these models over the other. So it becomes very time-consuming to fit all those to the data. So we try to make progress. And I'll argue that for the context in which on which I'm focusing, that is that of structure formation, cosmological observable, so we are on the cosmological scales, most of those models that I just showed in that branch are very well absorbed in this which is known as Hordesky gravity, or also generalized Galileons. Now, this is a way of writing the most general action, this most general theory that you can have for a massless tensor, the usual thing, the graviton, the usual thing that sources gravity in your standard scenario, plus a scalar field. And you want that scalar field to have equations of motion that are at most second order, because otherwise you run into troubles. There's not much you can do. And this Lagrangian is a very nice way of organizing your possibilities. And now you see that our ignorance goes, at least looks more ordered. Before it was this jungle of models. Now there is some ordering, some hiding them here and there into 4 free functions. Of course, they're a function of a scalar field and its kinetic term. X is the kinetic term. So you can argue whether I've made progress or not. But at least I have some guiding principles. And why am I considering, you will ask, why am I considering just basically a scalar tensor theory? Why am I just adding a scalar degree of freedom to my graviton? It's true, I'm doing just that. I will argue that other models that seem more exotic, like giving mass to the graviton or introducing higher dimensions, for the range of scales and observables that I'm interested in, will mostly show up in this form. And that's exactly how this Lagrangian was rediscovered. So in 74, Hordesky brought in an independent way, but then it was rediscovered in 2000 and something as a sort of limit of higher dimensional theories of gravity. So I will argue that we have pretty much a lot in there, and it's nicely organized, but still, if I face data, I have 4 unknown functions of time and of the scalar field and its kinetic term. So we are still not that happy. So we try to go further back and to what Jérôme Glazes, who is one of the authors in the first papers of the theory that I'm about to show, like to call building blocks. So there is a paper that is the building blocks of dark energy or something like that. So what are they? Okay, now you will definitely say that it's getting worse. But still, I'll try to argue that I'm making progress. And I'm making progress. Marco doesn't agree. I'm making progress because I'm trying to rely on some physical arguments of what I could have and could not have, still with the underlying assumption that I want to have a dynamical degrees of freedom out there, my graviton, massless graviton, and 1 scalar degree of freedom. Now, this is a horribly looking action. I've gone in what is known as the unitary gauge. So I do have a scalar field, and you're very used to see the scalar fields in this phi. But I have adjusted my coordinates in such a way that I absorb basically the scalar fields and its perturbation in the time coordinate of my system of references. So I've adjusted my so-called spatial hypersurfaces to coincide with uniform field hypersurfaces. That's just one trick to have your action containing only geometrical terms. The Ricci scalar, the time component of your metric, things that are related to the extrinsic curvature of your spatial surfaces. And now it gets very technical. But the whole point is that this unitary gauge gives you a nice language in which to identify all the operators that you can write there with some limitations. You want 1 scalar degree of freedom, you want second order equations of motion, and you are treating linear perturbations. You are happy with linear. You leave the nonlinear to Marco. So, and okay, so you go up to quadratic order. Why do I have loose indices? I have only time loose indices. That's because I basically given up time diffeomorphism invariance by choosing my spatial hypersurfaces to coincide with those of the scalar field. And so I can write my action up with all the geometrical objects that are invariant under three-dimensional spatial diffeomorphism. Okay, that's a very technical, and I think I'll skip this slide, which is making it even more technical, but it's trying to explain how you define this unitary gauge and what are all those objects. I'll go through this tomorrow. Hopefully you come after seeing this slide. So, okay. So why do we like this action? Why did we think of using it for cosmological test of gravity? Because soon after, it was Filippo Vernizzi and Paolo, was Paolo in the original? Federico Piazza, and there were people also in Cornell. They brought up this EFT of dark energy. Creminelli was beyond the EFT of quintessence. At that time, we were working heavily with CAMB, this Einstein-Boltzmann software to look at your perturbations from early times to today, right, and fit your theory to observations. And in particular, we were playing with MGCAMB, the version of CAMB that uses mu and sigma. We jumped immediately on this, and it was an excruciating exercise, really a pain, but it worked out, to implement the CFT theory in CAMB. Why did we do this? Because we strongly believed that it was going to improve significantly with respect to the status in which we were of using only mu and sigma. And there's many arguments of why it did that. The one that I want to give is that it is a nice way of, I have already sort of said that, but it's a nice way of organizing all the things that you can do. And you know, those functions in the action, those red functions, as you gradually turn them on, so you include more operators in your action, you gradually make your theory more and more exotic. So you start from Einstein-Hilbert action, that's the simplest. And then you start opening those other, and the thing you can do is to give a dynamics, whatever is source in acceleration. You can non-minimally couple to gravity. You can give it a non-trivial kinetic term, and it gets more and more complicated. So you have all the models in there. And the other thing that I want to, that I think is a very good aspect of this theory, is that you have an action, and as you know, from that action, you can study the stability of your theory. You can expand it to the quadratic order in the perturbations. You need to do some math because you need to isolate the truly propagating degrees of freedom. There will be some spurious degrees of freedom that you need to remove. But after you do that, not surprisingly, you are left with an action of this form, a massless graviton, and there are some coefficients. Here you have a scalar degree of freedom. There are some coefficients in front of the kinetic term, the gradient, and so on. And you know that to the positivity, for instance, of those coefficients, you can associate some conditions of stability. It's in a very simple way, you can think of looking at your harmonic oscillator, starting from the Lagrangian for it, and depending on the signs that you have in front of the terms in the Lagrangian, you will have exponentially growing or oscillating solutions for your harmonic oscillator. So that's a very simple case. It gets more complicated in here, but there are different conditions. Some are commonly agreed upon. Some are less conventional. We can think about superluminality and things like that, whether you want to impose it or not, to avoid superluminality or not. But there are some conditions such as ghost that are associated to the negative kinetic term and so on that we could all agree on, perhaps. And they have an important effect in guiding us about what we can do. I had 5 minutes? Yeah, okay. So now whenever I talk about this, I always get questions about these instability conditions and the fact that this is an effective field theory and whether I can expect to cure those instabilities with higher order operators, etc., and what is the cutoff of this theory and so on. So I want to give, preventing those questions, I want to give a very practical example of how we are using this EFT and how we are using these stability conditions. So we are using it as a sort of nice parametrization of all that gravitational landscape, right? But in mind, we have cosmological observations. So let me go to that famous example of the phantom divide. There was a very nice paper by Paolo Creminelli and collaborators showing how you can cross the so-called phantom divide, which is W, the equation of state being smaller than -1, without running into instabilities with your theory. You can do that, but there's a price that you have to pay, and you have to remember about that when you study perturbation. If you use cosmic microwave background, weak lensing, etc., to put constraint on W0 and WA, you have to be at least aware of what you are doing in terms of choices of your theory. So here I start from a very simple action for a scalar field, its kinetic term, and I look at perturbations of this scalar field. I like to absorb it in the coordinates, in my system of coordinates, right? But pi, think of pi as the perturbation to the scalar field. I have a standard kinetic term, and I assume that my action here depends only linearly on x. If that's the case, and you look at the quadratic action in the perturbations for the scalar field, this is what you get. And then you see that in order to make sure that you don't have a negative kinetic coefficient for the kinetic term, you have to basically have 1 plus WQ positive. So W cannot be smaller than -1, otherwise with this simple model you will run into a phantom regime. Of course, you can say, wait, but I have a more complicated P. It is nonlinear in X. Let's assume I have a P of that form. Yes, but that will bring new terms in your action. And in particular, it will bring such a new term. It takes you away. It solves your problem, right? It allows you to go to W smaller than -1. It gives you wiggle room to go to W smaller than -1, but still not making this coefficient negative, depending on, of course, there are scales, etc., that you need to fix. Fine. So we can cross the phantom divide. There is the parametrized post-Friedman thin income that allows you to do it and forget about any problem. You cross without issues with singularities, etc., that regime. But you have to remember that if you are allowing that from a theoretical point of view, for instance, by introducing this operator will affect your large-scale structure, will affect your clustering. So you're abandoning the simple quintessence model. And it's fine if you use Supernovae to look at this, but if you look with cleansing data to constrain W0, WA, and you allow the phantom divide, you have to tell me how you allow that phantom divide. You do it either introducing an extra operator, and then you have to take it into account in the clustering, or you're doing it perhaps going to multi-field. But so it's very important to keep it in mind. And that's, I skip this, but that's when talking with our colleagues that in Leiden, at the Leiden Observatory, they lead the kids experiment on weak lensing. That's why when we did this exercise, they were going in the phantom region, and we were asking which dark energy is it. Okay, I think I went a bit slow, but that's I hope I gave the flavor of what we are trying to do. It's using this action to learn about what we are allowed or not allowed from the theoretical point of view, and then eventually, and now I'm going to do something that is really annoying, I'm going to fast forward. Oh, there you go. And then eventually project what the theory allows me to do or not into the phenomenological plane of those functions that I show at the beginning. So this is an example. Using EFT, I explore all the theory space, but I make sure I obey simple conditions of stability. And then for all those models, I create 10 to the 6 models. For all the variable models out of those, I actually create 10 to the 8, and then I go down to 10 to the 6 with viability conditions. I project them on my phenomenological plane. I ask myself, what is the typical lensing pattern and clustering pattern that I expect, for instance, in the broad class of Hordesky gravity? And the interesting thing is that you see, so this is looking at the boxes for mu and sigma. At the center, you have lambda CDN. They're equal to 1. And I repeat all these different boxes going ahead in time. So here we are today, and going from very large to smaller scales. Forget the top one. That has to do with quasi-static approximation. Let's not worry. But you see that my 10 to the 6 Hordesky model if I look at them from the point of view of phenomenology, they're not so spread. They tend to align, and we had actually a theoretical argument for why they would do that. And they tend to align on this diagonal. And there are regions of this parameter space for mu and sigma where you are not allowed to go because of instabilities. There are other regions where you are restricted by what we know already from local test of gravity. So that's what we call theoretical priors, and I'll finish by saying that we use this EFT action to sample my, for instance, Hordensky or whatever. I can go beyond that, my models and what the theory allows me to do, but then we project it on those functions that we think are the best to make contact with data. So mu, sigma, and w, because they're more directly linked to what you observe and what you measure out there. And then that goes to the question that Rogerio was asking this morning. So we can start learning what we expect for this function from the theoretical point of view. And that's just pictures, right? I mean, it's just plots, but it's, we can do something more technical. It's again just pictures and nice colors, but these are covariance and correlation matrices for the function mu, sigma, and no, this is for one of them. I think it was for mu, if I remember correctly, looking at different subclasses of models. Never mind about that. But looking at the correlation, the covariance matrices, this is already published. I should have appended it. So why do we go through this excruciating exercise of creating these matrices? Because we want to combine them with the data covariance matrices in such a way that we sort of input theoretical priors. They have to be mild. They cannot be too strong. But you want to combine them in the form of theoretical priors with your data analysis. And this, I promise, is really the last slide. So it's a more pictorial version of what I showed before. Now I'm focusing on the snapshot at today, redshift 0. I pick one scale representative. I think it's something like k of 0.01. And again, looking at sigma and mu. So this tells me how much the clustering departs from lambda CDM. And this tells me how much the lensing pattern departs. Lambda CDM is here. And as I showed, there's a big region where you cannot go with Hordensky if you want to satisfy local test of gravity. There's another big region where you cannot go if you want your theory to be stable. And the other interesting thing, so that leaves you with the blue. There's further progress that you can make if you take into account what gravitational waves have told us about Hordensky gravity. Now I have this action. I can take into account what information I've gotten about the tensor from the propagation of these gravitational waves. And the effect, which seemed to be terribly drastic, it's there. It's very interesting. And what it does, it narrows even further your models on the phenomenological plane. So there's not much less left out there. But there is a very specific pattern that Euclid might look for instance. You expect mu and sigma to be basically equal. Not equal to 1 necessarily, but basically equal, which means no anisotropic stress induced by your theory of gravity. OK, so I hope I convince you that where we are trying to make progress, and we think that the right direction to go is to combine this more popular and phenomenological approach, which is great, very flexible, very close to data, but has limitation from the theoretical point of view, to sort of help it with this EFT, and this is an alternative EFT that you might have seen in the literature, and I'll talk more about it tomorrow. And they all have their pros and cons, but I think the winning thing will be from combining them. One is very close to data. The other one allows me to inject theory. So I want to incorporate physical principle into my data analysis. And I think that will allow us to make progress. And hopefully, what I would really like to be able to do is to implement non-parametric reconstruction of my theory. Rather than making parametrizations for those functions that I want to fit to data, do what is called as non-parametric. So I really sort of bin them, declare ignorance, and let data tell me what they want to be, but I have to give some guidance from theory in order for that process to converge. So that's all we are trying to do with EFT, and I'll stop here.
Thank you, Alessandra. So we have some time for questions.
So I actually have a question about that action and stability. So, well, action, question of comment, I'm not sure. So the point is, I think one could consider different frames. So for instance, you noted there that that was a Jordan frame. And my question, I think actually there are probably two scalars one could introduce, because you also consider G00 separately. So probably you could rescale both G00 and Gij independently. I'm not entirely sure. But the point is, I think depending on frames, the stability conditions might be different. The reason I say that is because, I mean, I just recently read a paper by Kovtun about the same issue in hydrodynamics, where he showed that different frames, like the Landau frame versus some other frames, involving nonlinear field redefinitions, have different stability properties. So I believe that if you're restricting to just if you're imposing some stability condition, you have to be aware in which frame you are, and perhaps look for a frame where that condition is less restrictive. So.
Yeah. Okay, I would definitely agree with that, yes. It's a very tricky business, even within one frame. But also, yeah, this thing, and some of the conditions, you're right, I put myself in the Jordan frame, so there's an assumption in there of universal coupling, or about the fact that I focus on dark matter. We can, and some of the stability conditions, for instance, if you work out speed of sound and you look at the gradient, they depend on matter, on your matter component. So I totally agree, yes. There's a lot of work to do, and thank you for pointing that out, yeah.
So I'd like to understand better this discussion about stability, because I thought the stability condition in one frame, the condition is different in the other frame, but if you do the proper transformation, they're equivalent, not?
Well,
so is there an issue or not? Is an issue on transformation of the condition?
It's I think it's a very subtle issue. I never look at the stability condition in a different frame than the Jordan one. But what I can say that is, as I was saying, is that, for instance, the speed of sound that you need to work out for certain of the stability conditions, you would think your scalar degree of freedom that you introduce will have its own speed of sound. Actually, it's speed of sound, once you do the proper diagonalization and you make your fields canonical, do pick up contributions from matter, from the different matter components. Now, I'm not sure what I'm not sure what happens if you start allowing for universal coupling, and so it starts, first of all, to be difficult to identify a frame. And yeah, I'm not sure what happens if you go to the other frame and you mess up with the couplings with matter. Yeah, the honest answer is I don't know, but yeah.
I want to ask about stability, but I want to know about unitary gauge. It looks maybe strange to me. You have 1 over x in your unitary gauge.
What do I have?
Yeah.
So yeah, that's just to identify the vector, the unitary vector orthogonal to the hypersurfaces of uniform.
What do you do if phi is
field.
constant?
No,
and mu is not defined if phi is constant. So
that's how you absorb, right? No, I mean, then you specialize that's the way you start from your action with the scalar field, which is not constant, right?
I don't know, why can't it be constant? If you're doing an effective field theory.
No, it's not a constant, you have a dynamical scalar field, right?
Yes.
And that's also behind the fact that I'm breaking, sort of spontaneous is breaking with the perturbation of the scalar field, my time difference is invariance.
So this is not an effective field theory, it's something else.
This is, well, indeed, you should call it effective theory more than field theory. No, yeah, so it's a bit of a stretching of what you are used to as effective field theory in quantum field theory, okay? So there's many questions that become difficult to answer when you apply it like this to cosmology, and also cut-off scales and stuff like that. But yeah.
Okay, thanks.
In the plots that you showed the correlation between mu and sigma, what's the difference in the upper ones? Because you have the quasi-static approximation not as good as the exact.
Yes. So that was, so with our code, when we take whatever theory in that action, EFT, and then we calculate perturbations, we evolve them, and then of course once we have the solutions for the perturbation, we can calculate mu and sigma, right? That's if you do it with the full dynamics, with your Einstein-Boltzmann solver. And those are the red points. I can do the thing analytically, sort of. So I can go in the quasi-static regime, and beautifully all time derivatives drop out. I have algebraic equation, and it's a lengthy exercise, but you can find analytical expression for mu and sigma. They will be ratio of polynomials in K-square. And so in black, that's what I'm plotting, the quasi-static prediction for those. And you are right. So here you don't see any difference. Up here you do see quite some difference. We are on pretty large scales, though. So this is giving me an idea of the horizon at which, the new horizon that I need to take into account for these theories in order for the quasi-static approximation to be valid, which is smaller than the standard horizon that we use, right? So now, there's a lot of, you should take this with a grain of salt, of course, because as much as I like to sell it as being very general in sampling Hordesky, I do have to choose strategies to sample that action. And in doing that, I tried many different expansions, but I sort of implicitly introduce some length scales in my choice of those parameters. And that will impact the sort of characteristic mass scale of this theory. So I'm sort of myself determining a little bit the scale at which that breaks. So it's not totally generic.
So this modification of the the equations for the scalar perturbations with mu and sigma. So it seems that when you do that, you are assuming modified gravity theories that don't couple vector and tensor perturbations at the linear level. So you automatically neglect them. So what happens with this kind of theory? Do you have bounds on them, or you don't care because they don't?
No, well, it's not that I don't care necessarily. Am I still on video? No, kidding. I don't know about those, how to model. I've been talking with Lavinia Heisenberg, for instance, works with, like, she does generalized Proca theories, where you have vectors coming into the game. And we were discussing how to repeat this exercise for those theories and see, do similar things to this. But yeah, I don't know. You're right. I'm not necessarily restricting myself to modify gravity, because I told you can reabsorb the coupling, but you can reabsorb the coupling if you have only the scalar field around. So if you have vectors, yeah, I don't know.
More questions? I have one question. So what are the prospects of going nonlinear or mildly nonlinear? Sorry.
I've invited Marco to Leiden.
Yeah.
So, no, so there's some people in Paris that are trying to combine EFT or large-scale structure with EFT of dark energy. I don't know much about that. I've been interacting with people that work with emulators. And we have been doing some third-order Lagrangian perturbation theory for this more generalized action, and try to provide them a very accurate linear input plus this third order to try to go a bit beyond. And that's more or less where I am at. So yeah, but that's the new, that's the elephant in the room, and yeah.
All right, so I don't see any other questions, so let's thank Alessandra again for this very nice colloquium. So there are refreshments out there, and for the students of the school, we should get back at 4 for this sorry, for discussion.